In this tutorial, I want to introduce some concepts related to the chemical bond. And included in that discussion is the idea of valency. So, what is a chemical bond? Well, that discussion has been going on for a couple of centuries. Once it was realized after Dalton's atomic theory that molecules form from the attraction of one atom for another and the way they bond to one another to make compounds. And then during a chemical reaction, the atoms just swap partners. The discussion from then on has been in the terms of what is the force, what is the bond that holds atoms together. What we've discovered is, and it's logical, that when two atoms approach each other, because we understand now from Rutherford's work that the atom is best modeled as a nuclear arrangement, where the protons and neutrons are contained in a very dense nucleus, and the electrons are in the space surrounding the nucleus. So when two atoms approach one another, the first thing they see is electrons. And that's where the bonding occurs between electrons of two atoms. So we're going to discuss the different types of bonding. One is the ionic bonding. And it gets its name from the fact that when two elements approach one another, one of them transfers electrons to the other, which makes that atom more negative, and the one which loses electrons becomes more positive because it's lost that negative charge. When they first approach one another, they're neutral because they have the same number of protons and the same number of electrons. But if you remove or add electrons, you unbalance and you produce ions, and then positive ion attracts negative ion. The other type of bond is called covalent. The covalent bonds occur between atoms that don't have a strong enough attraction compared to one another to remove electrons from one atom to the other. So their solution to the problem is to share electrons. That's called a covalent bond. Just as a side note, historically, the best explanation for the nature of the chemical bond was proposed by Linus Pauling in the late 40s, actually. He published a book by that name, Nature of the Chemical Bond. And that, in addition to the research that he had done and the way he explained the way the chemical bond behaved, he was awarded the Nobel Prize in Chemistry in 1954. Okay, the ionic bond. I already mentioned that when you transfer one electron or more electrons from one atom to the other, then you unbalance the charges. And one becomes more positive, one becomes more negative, and then the attraction is just simply positives attract negatives. It's an electrostatic description. Whereas the covalent bond refers to sharing electrons. And when atoms share electrons, they share them in pairs. Now, sometimes one electron comes from one atom, another electron comes from the other, which forms the pair, and that's a bond. On some occasions, one atom approaches, and the other atom provides both electrons for the bond, but they still share the electrons. there's a difference between ionic compounds and molecular compounds. For ionic compounds, like say we have sodium and chlorine, right? Table salt, sodium chloride. We would represent them as a collection of ions. And that array of positive and negative ions, which go on for as big as the crystal is, right? In 3 dimensions, this way, that way, and inside, in and out of the board. So we can't describe them as, when we say this, that represents the compound sodium chloride. We have to recognize that it's not just one sodium ion and one chloride ion bound together, independent of the other ions. It doesn't happen that way. It happens as what we would call a crystal matrix of positive and negative ions. Those are ionic compounds. Molecular compounds result from sharing electrons. And when electrons are shared, you get a compound that behaves as a single unit. The examples, water, right? There you have 2 hydrogen atoms and 1 oxygen atom bound covalently into a single unit. So these water molecules exist independently of all their neighbors. Carbon dioxide would be another example, or carbon monoxide, right? The bad one. Those are molecular compounds. And remember our discussion of the periodic table. Yeah, we have discussed that. The periodic table is divided into 2 sections, nonmetals on the right, metals on the left. Covalent compounds are always formed from 2 or more nonmetals. And ionic compounds are formed from a metal and a nonmetal. Let's see. I have to introduce this idea, but we're not going to dig into it too deeply. And that has to do with when we discuss ionic bonds and covalent bonds. Most bonds of any kind, ionic or covalent, have some character of both. The only type of covalent bond that has no ionic character to speak of are those that are bound between 2 of the same elements, like dinitrogen. We would say that has no ionic character. And the it would take another hour of discussion to actually tell you that there is some ionic character, but it's not permanent, right? So don't be too concerned about that. It's just that the vast majority of bonds, whether they're ionic or covalent, have some components of both. Now, in order to simplify the discussion and the understanding of the chemical bond, we introduced this concept called valency. And it has to do with the electrons that we believe are the ones that participate in the bonding. These valence electrons are the ones that are furthest from the nucleus, and they're the ones that are approached and participate in bonding between 2 atoms. So we have things like, let's see, let's take a simple one, like fluorine, right? The fluorine atom we'll have 2 electrons in that orbital. And then in this orbital, it will have, let's see, 7. It'll have 7 electrons. 1, 2, 3, 4, 5, 6, 7. Because it has 9 protons and 9 electrons. So when this atom approaches another one, and there's going to be a bond, these are the electrons in the outermost shell that participate in the bonding. Those are called valence electrons. All the others closer to the nucleus than the valence are called core electrons. And we generally don't consider those in terms of bonding. Now, there's one caveat here that you don't need to be concerned with. I just wanted to introduce you to the idea so that if you ever hear it, then you won't be completely ignorant of the concept. This idea of valency is attributed to and is central to one of the theories of bonding called valence bond theory. And what I've discussed so far is central to that idea. In a more advanced model, the molecular orbital theory requires that every electron in every atom in the molecule participates in the bonding. Okay. And we don't have time to discuss that now. I just thought I'd introduce that idea, and you can take it for what it's worth. All right. So remember that electrons in their position outside the nucleus, the further they are away from the nucleus, higher their energy, right? Lower energy in close, higher energy further away. So those that have the same energy, they're in the same orbital, are considered the valence electrons. Now, there's a rule that you may have been introduced to perhaps in biology class or even in anatomy and physiology. It's called the octet rule. And I'm going to talk about that in more detail in just a minute. But it's restricted, this rule is restricted to representative elements or noble gases. And these elements are in the periodic table on either the far left or the far right of the periodic table. And the transition elements in the middle don't participate in this rule. And with this periodic table, we see that the first two, the alkaline metals and the alkaline earths, and then the boron group, the carbon group, the pnictogens, the chalcogens, the halogens, and the noble gases are all part of the representative elements. And the upper levels from, say, calcium back are predominantly the ones that respond best to this rule, this octet rule. And I'll explain what the octet rule means in just a minute. These representative elements, if you need to know how many valence electrons are associated with each of the elements, you just look what position does it occupy in the periodic table. So this first group here, right, the alkaline metals and hydrogen have 1 valence electron. And the older system of labeling the groups, this Roman numeral system, will tell you how many, or you can count from left to right. The first group always has 1 valence electron. Second group has 2. Starting with boron, we skipped over the transitions. Boron has 3, carbon has 4, nitrogen 5, oxygen 6, and fluorine 7. And then the perfect noble gases have 8. That's the octet. So, what's so special about the octet? Well, the noble gases are very stable. They typically do not react with any of the other elements. Now, there are exceptions. We've been able to force them to react, but generally speaking, noble gases don't react. They're often called the inert gases. So we showed these elements with dots around them. You see that? Dots. Those are Lewis symbols or Lewis dot structures. And I'll go back. Let me go back one. See? So if carbon has 4 valence electrons, we put the 4 dots around them. There are 5 around nitrogen. You see 5 dots. That G.N. Lewis was an American chemist who proposed this method to help us track the movement of electrons and bonding. And it works fairly well. So lithium would only contribute 1 valence electron to a reaction. All right. Okay. So you can either look at the Roman numeral for the number of valence electrons or count from left to right. And skipping the transition elements, left to right, just 1, 2, 3, 4, 5, 6, 7, and noble gases. All right, so determine the number of valence electrons in each of the following elements. Calcium, where's calcium? There's calcium right there. It has 2 valence electrons. Okay. Sulfur's over here. It has 2, 4, 6 valence electrons. Carbon has 4. Okay, it's really that simple. Okay, we can generalize about valence electrons. Representative elements in the same group have the same number of valence electrons. And this is leading us toward the idea that members of the same group behave similarly, chemically speaking, right? In terms of chemical reactions, members of the same group behave similarly because they have the same number of valence electrons. The number of valence electrons for these representative elements is the same as the Roman numeral in the old style periodic table. Now the periodic table the modern versions have numbers across the top listing from 1 to 18. Right? That doesn't give you the information that we're looking for here. So if you don't see the Roman numeral system, then just count from left to right, and that'll tell you how many valence electrons are there. The maximum number of valence electrons in this system is 8. That's the octet. That's considered perfect. Okay, so back to the octet rule. Certain arrangements of valence electrons are more stable than others, and their stability is associated with the number of valence electrons in the noble gases. The noble gases are very stable, and we envision elements, when they react with one another, they're trying to attain octet configuration of their electrons. That's the driving force for the chemical reaction. So that's, generally speaking, our octet rule. Elements tend toward obtaining an octet either by transfer of electrons or by sharing. Okay, so to produce this noble gas configuration for each of the atoms involved, we have to move electrons from some place to another. If we do it to form an ionic bond, that is a positive ion versus a negative electron attracting one another, Then we would transfer electrons and complete the octet for the receiver and complete the octet for the contributor. All right. We have a special name. Negatively charged ions are called anions. They have gained one or more electrons. And by doing so, they have unbalanced their electric charge. Right? They're neutral. To begin with, they're neutral because they have the same number of protons as electrons. Right? This would have 9 protons and 9 electrons. Right? So it's neutral. Fluorine tends to accept electrons. So if it accepts 1 electron from somewhere, now it has 8 electrons. Oh, excuse me, in the outer shell, or 10 total. Right? 10 valence electrons now, because it accepted 1. So now we have 10 negatives and 9 positives, which means we have an excess of 1 negative. That means this fluorine will be that 1 negative charge. That's an anion. If that electron came from a sodium, sodium is 11. So sodium would have 11 here, 11 protons, 11 electrons. Then if it gives up an electron, right, that's what metals do. When they come in contact with a nonmetal, they tend to give up electrons. So now we only have 10 electrons. So that means 1 positive. That's a cation. And the golden rule for forming ions is do not touch the protons. Right? Remember previous video. If you change the number of protons, you change the element. We don't want to do that. We just want to form an ion. So you do it by adding or subtracting electrons. This is an artist's rendition of what happens to a sodium when it loses an electron. And this is the chlorine that could gain the electron. Right? So sodium's a metal, chlorine's a nonmetal. Chlorine will accept an electron and become -1. Sodium will lose an electron and become a +1. Okay. So why does sodium only lose 1 electron? Because if it loses 1 electron, look what happens. It has, what did I say, 11? Has 11 electrons. If it loses that 1 electron, then it only has 10 electrons now. If we back up to neon, right? If we back up to neon, it has 10 protons and 10 electrons. So it has a perfect octet. Well, if sodium loses an electron, now it has, in its valence shell, it has a perfect octet, like neon. And that makes it very happy. Whereas chlorine, if it gains an electron, then its electronic configuration looks like argon. And that's a perfect octet. So sodium is happy to give up an electron. Chlorine is happy to accept one because each of them acquires a noble gas configuration. All right, so this is characteristic of any of the elements in our representative groups. What they're trying to do is look like noble gas configuration of electrons. So all the elements in the first group, if they lose an electron, then they look like the noble gas that's in the period above them and at the very end. So lithium would look like helium. Sodium would look like neon. Potassium would look like argon. All they have to do is lose 1 electron. Now, magnesium would have to lose 2. If magnesium lost 2 electrons, its electronic configuration then would look like neon, and it would be happy also. That's why the elements in the first group, the alkali metals, always produce a +1 charge when they form compounds. In the second group, the alkaline earths, they always form a 2+ charge when they react and form ionic compounds. Boron and aluminum, they would always lose 3 electrons and become 3+ charge cations. All right. On the other hand, if we're on the other end, say the halogens, all they need to do is gain 1 electron, and they look like the noble gas right next door. Okay? So they would only acquire a -1 charge. But if oxygen did the same thing, it would have to gain 2 electrons. If it gained 2 electrons, then it would look like neon. So the halogens always acquire a -1 charge. Oxygen acquires, and its group, the chalcogens, acquire a 2- charge. The nitrogens, the nitrogen group, 3- charge. All right. Carbon group is different. Let's go back. Carbon, look, it's got 4 electrons, so it could either gain 4 electrons or lose 4 electrons. That makes it and its members of its group very versatile. These, when these elements react, they can form a mixture of different types of bonds to arrive at their noble gas configuration. All right. Metals donate electrons, nonmetals accept electrons. Electrons are lost by metals. The same ones then are gained by the nonmetal, and the formation of a positive cation and a negative anion then sets up the electrostatic attraction. And the force of attraction obeys all the rules proposed by Coulomb in the 18th century. I think it was the 18th century. And this is what it would look like. See, this sodium would donate an electron to chlorine. Now sodium is deficient in a 1 negative, which makes it a +1 charge. Chlorine acquired an electron, making its octet, and we get a positive-negative attraction. Now, because sodium lost that electron, we don't show the next level down. But the next level down will look like neon. For instance, in this case, oxygen needs to acquire 2 electrons. So it gets 1 from one sodium and 1 from the other sodium. That's why 2 sodiums are required to satisfy oxygen's demand. And then the formula for this compound would be Na2O. Now, for ionic compounds, remember I mentioned that ionic compounds are an array of positive and negatively charged ions. So when we say Na2O, we're actually saying this is the simplest whole number ratio of ions in the compound. The ionic compound itself will be an array of sodium and oxygen ions. So it could be Na 4 billion and O 2 billion, right? But that's a little unwieldy. So we simplify it to the nearest whole number ratio so that the charges balance, right? 2 positives, right? 2 positives balance 1, 2 negative. Similarly, calcium can give up 2 electrons, and chlorine only needs 1 each. So 1 calcium will balance the charge of 2 chlorines. And that's why we have a formula now of 1 calcium and 2 chlorines, because calcium 2+ needs 2 chlorines to balance the charge. Now that compound is considered neutral. All right. That's enough for this discussion. Come back for video number 9 and we'll continue.